So in the last video we looked at the structure of atoms. What we're going to do now is have a little look at how we classify the more fundamental particles. I know that at GCSE you're told that the smallest things are protons, neutrons and electrons. And that's not quite true. Electrons definitely can't be divided up into anything else, but protons and neutrons can be. They can be divided up into quarks, which I mentioned a couple of videos ago. So what we're going to look at is how we classify all these different new particles that we're going to meet. And a lot of this comes from what's called the Standard Model. The Standard Model says that there are 12 fundamental particles and they can be split into two groups. So we've got leptons and we've got quarks. And within the leptons and the quarks we've got first, second and third generation. They're kind of paired. They have slightly matching properties in terms of charge within each generation, and then as we go up the generations the mass increases. Now the ones that I have coloured in bold are the ones that you are expected to be aware of for the exam, but it seemed a bit silly to miss out all the others if we're going to talk about the Standard Model. So I will mention them, but you just need to make sure you definitely remember the properties of the ones that are in bold. So our leptons are electrons, which you're already aware of, and matched up with them are electron neutrinos. Neutrinos are just tiny particles that are whizzing through us, millions of them at a time, and we can't even feel them. They're just very, very small mass, and they have no charge either. Second generation we have the muon, which has got the symbol mu, and a little minus, and the charge of a muon is the same as the charge of an electron. It's just got more mass. And matched up with a muon is a muon neutrino, which is just a neutrino that has a bit more mass than the electron neutrino. The symbol for these is the slightly funky V, then with the lowercase either E or mu. You can for the most part just put the italicized V and you'll be fine with that. Third generation then we've got tau, which again has the charge of an electron, and the tauon neutrino, which has no charge, just a bit heavier. In our quarks, these are the things that make up bigger stuff. Our first generation we've got up and down. So an up quark has a charge of plus 2/3 of an electron, and a down quark has a charge of minus 1/3 of an electron. Now you may be thinking that it's weird that we've got these fractions of the charge of an electron, particularly when I've told you that charge is quantized. And the smallest packet of charge we can get is equal to the charge of an electron. But that is still true because we will only ever find these quarks in groups when they are making up other particles. And when they make up those other particles, their charges will always be combined so as to give a whole number of charge of an electron. So that is still true. So first generation is up and down, and that makes up basically everything we interact with. Second generation are charm and strange. Third are top and bottom. So again, charges just match up, plus 2/3 for the top, minus 1/3 for the bottom, and we just get heavier as we go. Now strange are just a type of particle that have got an extra new property, and that property is just called strangeness. Don't get too hung up on it, it's just the name, and it's like charge is just the name. Things either have charge or they don't. Well, things are either strange or they aren't. It's as simple as that, really. It's just whether they react in certain ways in certain situations. Okay, so those are leptons and quarks. What we do is we can split all particles and antiparticles, which I'll talk about in a second, into two groups. Those two groups are hadrons or leptons, and that just completely depends on whether they interact through the strong force or not. So if they do interact through the strong force, they're hadrons. If they don't, they are leptons. Now we already know leptons, so that's fine, but hadrons are pretty much everything else. So protons and neutrons, which are in the nucleus, so they must interact through the strong force, and also these particles called mesons. And mesons are particles that are just made up of two quarks, whereas protons and neutrons are made up of 3 quarks. But we're going to talk about this a little more in a second.
So, got hadrons and leptons. We can then split our hadrons into two further groups, and those two groups are either baryons or mesons. Now, the technical definition for a baryon is protons or particles that can decay into protons. So basically, for you, that's protons and neutrons. Baryons are also things that are made up of 3 quarks. Mesons are not protons and do not decay into protons. So an example for you there are K mesons and pi mesons, and they are made up of 2 quarks. So that is the difference between our baryons and our mesons. Right, the next thing we need to talk about is antimatter, which I briefly touched on. Antimatter is just the opposite of matter, basically. So every particle of matter has a corresponding particle of antimatter. And these particles of antimatter have got the same mass as the matter particle. They just have opposite charge if it's charged. And if the matter meets the antimatter, it would undergo what we call annihilation. And annihilation is where the mass of the particle and the antiparticle is converted into 2 photons. So the 2 particles cease to exist, and we just get two photons of energy emitted. So just to give you some examples of antimatter, we've got the antiproton, which is just a negatively charged proton. We've got the positron, which is a positively charged electron. We don't really say anti-electron, we just call it the positron. And then we've got the antineutrino, which is just the opposite of a neutrino, and it's something that's produced in beta minus decay. So we'll talk about that a little bit more later. So just some little notes on antimatter then. Basically all the particle properties are reversed, so there are uncharged antiparticles as well, so you can get an antineutron as well, because there are other properties that we don't need to worry about that can be reversed. Just because 2 particles have the same mass and opposite charges doesn't mean that they're a particle-antiparticle pair. And generally, when we write about antimatter to show that it is antimatter, what we do is we put a line above it. So here I've got a proton, this is an antiproton. Neutron, antineutron. My bar's a little bit off, I'm afraid. Then a neutrino and an antineutrino. And we do use antimatter in real life. We often use antimatter in PET scanners. In fact, we use it in PET scanners. We need it. It's how they work, which we'll talk about later. So antimatter is not this imaginary, crazy sci-fi thing. It is real. It is something that exists, and it is something that we use and harness on an everyday basis, which is quite cool, really. Okay, so that's it on our classification of fundamental particles. We're going to have a lot of look into these and all the different types and things that there are, so we can get comfortable with them and their properties. Okay, so that is it. Remember, if you have any questions, just ask.